In today's tutorial, we are diving into the fascinating world of face recognition. Whether you are curious about the technology behind unlocking your smartphone with a glance, enhancing security systems, or exploring the limitless possibilities of computer vision, you are in the right place. We'll explore the fundamentals of face recognition and take you through the implementation process, breaking down the code so that it is easy to understand. So without further ado, let's embark on this exciting journey into the world of face recognition technology. Let me demonstrate a brief preview of the face recognition application we will be building today. When the application is launched, it will attempt to identify faces, and if there is a match with a known face, it will display an ID card with information next to the recognized face. First, let me explain the application flow to you. As a prerequisite, we will gather images of known individuals and generate face encodings using a face recognition library. This library has a model trained for facial feature detection and face encodings. Next, we will read the video stream from the camera using OpenCV. For each frame, we will utilize the face recognition library to identify the bounding box for face locations and extract the face encodings for each face. We will then compare these encodings with the known face encodings. If there is a match, we will display an ID card with information next to the person's face. Open your favorite Python IDE. For this demonstration, I'll be using PyCharm. Go to Settings Project Interpreter, click the plus button and search for dlib, then install it. dlib is a modern C++ toolkit containing machine learning algorithms. Next, install face recognition to identify faces in a video stream. Afterward, install NumPy for efficient mathematical operations on arrays. Finally, install OpenCV Python for image processing and various computer vision tasks. Let's import the required libraries: face_recognition, CV2, NumPy, and OS. We will utilize the face_recognition library to identify faces in a video stream, CV2 for image processing and various computer vision tasks, NumPy for efficient mathematical operations on arrays, and OS for interacting with the file system. We will set up two variables, known faces dir and face ID card dir, and store the paths for the face images and face ID images directories respectively. We'll collect pictures of known faces and put them in the face images directory. Then we'll create ID card pictures for them and store them in face ID images directory. Next, we will use the list_dir function from the OS module to retrieve a list of file names from the face_images directory and store them in the known_face_image_files list. Moving forward, we will proceed to declare a list named known_face_encoding. In just a moment, I will explain the purpose behind this declaration. Now, we will iterate over each file in the known face image files list using a for loop and store each file's content in the variable known face. Inside the loop, we will utilize the cv2.imread function to open the image file. Subsequently, we will convert the image from the BGR color space to RGB using the cvt color function from the OpenCV library, and then we will store it in the variable known_face_image. This conversion is necessary because the face_recognition library follows a different pixel ordering, specifically in RGB format. Next, we will use the face_encoding function from face_recognition library with known_face_image as input. This function returns 128 dimensional face encodings for each image's face, which we will store in the known_face_encoding list that we created earlier. Notably, the encoding of each face will be stored at the same index position as it is in the known_face_image_files list. So let's understand what face encoding is. Face encoding is essentially a method of representing a face using a set of 128 computer generated measurements that are unique to an individual. This ensures that two different pictures of the same person would have a similar encoding. These measurements include distance between the eyes, the distance from the forehead to the chin, the distance between the nose and mouth, the shape of the cheekbones, the contour of the lips, ears and chins, among others. Now let's open a camera for video capturing using the video capture function of OpenCV. We will pass 0 as the index which corresponds to the default camera. This function returns a video capture object that represents the input video stream. This object can be used to read frames from the video input source. Next, let's retrieve the frame's width and height in the video stream by using the get function on the video capture object, passing 3 and 4 as arguments. Here 3 corresponds to the width property and 4 to the height property, and will store these values in cap_width and cap_height respectively. The loop while cap is open continues as long as the cap video capture object remains open and valid. Inside the loop, frames are read from the video source using cap.read, which provides the frame and a status indicating successful reading. If the frame was read successfully, we will process the image, otherwise we will exit the loop. We'll use CV2IMShow to display the captured image, followed by CV2wait key with a 1 millisecond argument. These steps are typically done after image processing to display the final image. The implementation of CV2wait key with 1 as an argument within the persistent loop generates an image sequence that the brain perceives as a cohesive and uninterrupted video stream. Next, we will flip the image by calling the flip function and passing the image as the first argument and the flip code as 1 in the second argument to flip the image around y-axis to create a mirror image. Then, as the first step, we will resize the image size using a scale factor of 0.25 on both the x and y axis. This will reduce the image size by a factor of 4, resulting in faster processing. Subsequently, we will convert the image from BGR to RGB using the CVT color function from the OpenCV library. This step is mandatory as face recognition library exclusively supports the RGB format. First, we will call the face_locations function from the face_recognition library and provide the image as an argument. This function returns an array of bounding boxes for human faces in an image, and we will store this information in the detected_face_locations array. Next, as the subsequent step, we will invoke the face encoding function from the face recognition library, passing the image and the detected_face_locations array as arguments. This function returns the 128 dimension face encoding for each face present in the image, and we will store this encoding in the detected_face_encodings array. We will use the Python's zip function to combine the elements of the detected face locations and detected face encodings list element wise. This will create a sequence of tuples where each tuple contains corresponding elements from the input lists. During each iteration, we will store the retrieved elements in the variable face_location and face_encoding respectively. Subsequently, we'll use the compare faces method from face recognition library. This function will compare the face encoding in each iteration with the known face encoding list that we prepared earlier. The method returns a list of true or false values, indicating which faces in the known face encoding list match the face encoding. We will store these results in the matches list. Next, we'll utilize the face distance function from face recognition library. This function will once again compare the face encoding in each iteration with the known face encoding list. For each comparison, the function will compute a Euclidean distance reflecting the similarity between the faces. A lower distance value indicates higher similarity. We will store this distance's value in the face similarity distance list. Moving forward, we'll use the numpy's argmin function on the face similarity distance list. This will return the index of the element with the minimum value in the list. We will then check if the boolean value at this index in the matches array is true. If it is, we have a face match. This is confirmed because the element at this index in face similarity distance list has the lowest value, and at the same index in the matches list there is a true value. Given that the matches and face similarity distance list originates from known face encodings list, which in turn is derived from known face image files list, this alignment ensures that the data at the same index pertains to the same face in all lists. Therefore, we can extract the face image file name from known face image files list at the index matched position and then apply OS path split text function on file name to get the name without its extension from the 0th index. Finally, we can extract the first name by using the split function. Now we will extract values from face location, which is essentially a tuple of detected face locations in the order of top, right, bottom, left. This values corresponds to y1, x2, y2 and x1. Next, if you recall, we scaled down the image by a factor of 4 to enhance processing performance. However, for display purposes, we need the original full-size image. So we'll resize and scale up the image by a factor of 4 by multiplying y1, x2, y2, x1 by 4. Moving forward, we'll create a rectangle bounding box around the identified face location using the rectangle function from OpenCV. We provide the image as the first argument, followed by 0.1 x1 y1, then 0.2 x2 y2. We specify the RGB values for the green color and set the thickness of the rectangle to 2. Similarly, we'll draw another rectangle just below the face location bounding box to display the matched person's first name. This time we'll slightly reduce y2 by 35 to position this box slightly above the bottom of the face bounding box. We'll use CV2 field function to draw a filled rectangle while keeping other parameters unchanged. To display the first name, we'll utilize the putText function of OpenCV. We'll pass several arguments in order, that is image original, first name, x1, y2 position to display the text above the bottom rectangle, and an offset of 6 pixels added to the x coordinate and subtracted from the y coordinate for precise text placement. We'll use font Hershey complex as font style, set the text size to 1, specify RGB for white color and choose a text thickness of 2. Moving on, let's calculate the width and height of the bounding box using x2 minus x1 and y2 minus y1 respectively. These dimensions will be used for the ID card display positioned beside the face bounding box. To avoid distortion, we'll consider half of the width. For the ID card display, we need to determine its position on both the horizontal and vertical axis of the captured image original frame. This will be done by calculating x2 plus width and y1 plus height, storing them as ID card horizontal axis and ID card vertical axis respectively. We'll then check whether ID card vertical axis is less than cap height and ID card horizontal axis is less than cap width, ensuring the ID card image aligns within the frame's height and width limit. If this is true, we'll read the image file corresponding to the matched face using IMRead. After resizing it to the previously calculated width and height, we'll store it as the ID card display numpy array. Finally, we'll place the ID card display numpy array besides the face bounding box within the image original by slicing the image original numpy array. Here, y1 to ID card vertical axis denotes rows and x2 to ID card horizontal axis refers to columns. This is where we'll paste the ID card display numpy array. To wrap up our code, we'll use the release function to free the resources of the video capture object and the destroy all windows function to close all currently open OpenCV display windows. Now let's test our code by right clicking and selecting run detect_faces.